Hi guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In my channel, I deal with the different aspects of mathematics and sciences, and this basically consists of various topics in mathematics, physics, chemistry, and biology. And we normally post a link of this playlist of these videos in our description boxes for various videos that we have already uploaded. So I'd like to request members kindly to check on YouTube, search Ernest Sciences and Mathematics TV channel, and subscribe to our channel and engage us on the comment section so that we can be able to have a healthy discussion on these various topics. So today, basically, we're going to have a second part of what we had looked at in our first video concerning the concept of Coulomb's law. Sorry for that. So this basically is going to deal with various, rather a number of analogous laws which are similar to Coulomb's law. And also we're going to look at ways in which we can be able to represent these specific forces in terms of vector forms. And that is going to close for us our discussion for today, basically, which are going to give us a clue on how we can be able to establish a relationship, or rather the similarity that exists between Coulomb's law and other analogous laws. So in our first discussion, we looked at this specific aspect of the Coulomb's law, and we said that the Coulomb's law basically is a statement that describes the forces between two electrically charged spheres, which are of course at rest, and which we had said that they consist of what we call a uniform charge. And of course, we have said that we are going to consider, sorry for that, this is uniform charge. And we had said that we are going to represent the distance between the two spheres by considering, of course, the center to center distance. And then we had said that we're going to also consider the aspect of forces between these two spheres, whereby we had represented force using F. And then we had said that the distance between those spheres are going to be represented by R, the center to center distance. And in considering this, of course, we had said that these uniform charges, or other charges, are going to be at rest. And therefore, also we had said that we had talked about the concept of a proportionality constant, which we had represented as a K, and in actual sense, which we had given us a reciprocal 4 pi epsilon naught, which is a permittivity, electrical permittivity. So therefore, this gave us a relationship which we wrote as a force is directly proportional to the square, rather the product of the charges of the two spheres. And of course, it's inversely proportional to the square of the distance between the two charges, which gives us a formula of representing Coulomb's law as the product of K and the product of the two charges and over the reciprocal of the square of R. So basically, this is an expression which is going to represent the Coulomb's law as per our first discussion. And therefore, we see that the works of various other scientists gave input into this particular case for Coulomb's law. And we're going to see that in trying to quantify different aspects of the charges that we have mentioned, we're going to see that there's going to be an input of Michael Faraday's and Robert Millikan's laws and the various other aspects of electrostatics, which basically deals with the concept of laws of attraction, which is, of course, in an essence, is going to give us the direction and other aspects of vector forms, which we're going to look at shortly in this specific discussion. So I mentioned the concept of analogous laws to Coulomb's law, and one of the laws that we're going to see being displayed or given in analogous form as Coulomb's law is what we refer to as the gravitational law. So the gravitational law, of course, is going to be given as, so let's consider this specific case. So the gravitational law is going to be given as the force between this specific, what we can consider as particles, is going to be the product of what we refer to as G. Of course, I'm going to elaborate on what that one basically refers to, and over the square of the distance between them. If you try to look at this, of course, we can see that there is an aspect of similarity, whereby the proportionality constant is going to be represented in this gravitational law using G, and then capital G, and then the product of the charges between the two particles is going to be analogous to the product of the mass of those two particles which are interacting in the gravitational law. And then we're going to see that this is going to be the square of the distance that is going to separate this specific aspect of the gravitational law. In this case, if you try to consider this one, this is a Coulomb's law, and this is a gravitational law. Now, in this particular aspect, we're going to see that there's going to be a slight variation for these two particular aspects of the laws, in a sense that the gravitational law is going to hold only for, of course, point charges whose sizes of the particles are much smaller than the distance between them, and that is going to be elaborate, of course, when we're going to have some problems which we're going to solve and try to quantify some aspect of that specific forces. And whereas the gravitational forces are attractive, we're going to see that the electrostatic forces can either be attractive or repulsive according to the Faraday and the Robert Milkan's aspect of the electrostatic forces for attraction and repulsion that I've mentioned in this specific aspect. So we can be able to represent this Coulomb's law and other analogous laws in terms of a vector form. And in this case, when I talk about the concept of vectors, we're going to, of course, have in mind the aspect of what we refer to as magnitude and direction. And we're going to see that basically this is one of the characteristics of vectors that we have looked at in one of our videos, especially on the concept of a vector analysis. So therefore, I'm going to consider this one also as one of the ways in which we can be able to represent the Coulomb's law and analogous laws. And if we are, of course, going to consider the aspect of two charges that I've mentioned for Q1 being at that specific point for these various two. So let's just represent that one figuratively using these two particles for Q1 and Q2. And if we try to look at this specific case, then we're going to, of course, represent this one using this assembly of two charges for Q1 and Q2. And in vector form, we said that we're going to use arrows in this particular aspect. So in any case, if I try to put them facing in this opposite direction, then therefore we're going to see that there's going to be repulsive forces which are going to be experienced between the two particles. And if, of course, we're going to consider the aspect of resultant forces, but in this particular case, I'm just going to use that illustration for that. So we can consider this one the distance between the two particles as R as I had indicated in my first case. So therefore, we're going to have two forces being experienced in these two ends of this specific assembly of these two particles. And therefore, we can represent the force from my left using this particular case. We say that force is a vector quantity. So therefore, this is going to be represented using those specific arrows. So this is going to be the force of 2 that is being experienced on particle Q1. And this is going to be a force of 1 being experienced by particle 2, which can be represented as such. Now, in terms of this equation, we're going to see that we had said that these are uniform forces, and therefore they are going to be similar, and therefore we can be able to represent the relationship between these two forces as the magnitude of the force of particle 1 on 2 is equivalent to the magnitude of the force of particle 1, sorry for that, particle 1 on 2. And this is going to give the relationship between these two particular forces which are being experienced by that assembly of two particles that I've given on that. Now, in some aspects, we're going to see that this particular radius is going to be represented as such, since it's going to stand for the, of course, the aspect of these two forces that I've mentioned in this particular case. Now, the vector form, of course, is going to be very essential in us trying to consider the forces due to assembly of more than two charges. And of course, we can be able to give individual representation of the Coulomb's law for the two forces that are given for F1, F2 on 1 and F1 on 2, respectively. So if we try to consider this specific case, then therefore we're going to have the force of this particular case, that is force of 1 that is acting on 2, and therefore this is going to be given us from the Coulomb's law. We have said that we're going to give this one as a permittivity, this particular value for K, and therefore this is going to be, of course, in conjunction with other aspects of the law that we are given is as a product of the charges, and then inversely proportional to the square of the distance between the two. And in this case, we have said that the square we are going to represent them using as R subscript 1, 2. And of course, this we're going to use a unit vector that is going to be given by this specific R 1, 2, given as such with that small hat in this specific case. So for us to represent this particular force that I've given for F 2, it's going to be given as such in form of an equation. But in that specific case, we can give also an example or an elaboration of this specific force, which I've given for F 1. So this is going to also to be represented as the value for K, and then this is going to be given as a product of Q1 Q2 over R squared. And then we're going to have that specific vector, which is going to represent what we refer to as the unity vector for that. And we'll say that this is the distance in reference to 1 for that specific radius. Now, the Coulomb's law that we have talked about in our first and second video is going to assist us, of course, calculate the distance between the two charges using this specific formula that we have given. So in any case, if we are given the value of R and other aspects like the charges or the force which is being experienced, therefore we can be able to make this one the subject of that specific formula and find the distance between these specific charges or charged particles. So that's one of the applications of Coulomb's law that we're going to see being used in some of our videos that we're going to encounter in electricity and magnetism and other gravitational aspects that we've talked about. And also we're going to see that it's going to assist us in trying to calculate the aspect of electrical fields. And of course, we're going to see that one later when we're going to do an analysis of point charges and other similar discussions. So of course, this is going to also contribute, apart from describing the distance and then the electrical field and the forces between the charged particles, we're also going to see that it's going to play a fundamental role in the development of what we refer to as electromagnetism, or the electromagnetic theory, which of course we're going to see later being explained in the concept of other videos on electricity and magnetism. Of course, this is going to form the last bit and the second part of what we discussed and the review of the Coulomb's law. And these are going to play a fundamental role in assisting us understand the different aspects of electricity and magnetism insofar as applications are concerned. So that is it for now, guys. Kindly check us, catch us in other videos, and also check in our description boxes for various videos which are related to these specific topics that we are discussing under the topic of electricity and magnetism. So that is it for now, guys. Bye. God bless you.